Welcome to the Cosmic Pie, Season 2, Episode 30. I am your host, Wayne Barkhouse.
And I'm Robert Moore.
Robert,
Uh-oh.
let's start this off right. We do have a live chat that's running, so
Yep.
feel free to use that feature. Put in your comments or your questions or complaints or anything else that you would
Yep.
like to share with us.
Like hopefully if you can't hear us or something like that, you put a comment in there,
And speaking about hearing us,
Uh-oh. Okay.
everything that we say, of course, are our own personal
yes.
opinion.
Our opinions, not the universities, not the college, not the department, just us.
Just
We're the
us.
guilty party.
We are. So winter has arrived, Robert. Have you noticed?
Oh, Lordy, yes. Today it wasn't that cold. It was only 18, but
Only. I
Yeah.
wish that was Celsius.
yeah, right? But it was quite windy.
It could be
out
worse.
there.
Could be Kelvin.
I don't think we would have this discussion if it were Kelvin.
No. But it would be nicer if it was 18 Celsius outside rather than Fahrenheit, obviously.
Absolutely.
And we're under a storm watch or something, I noticed too.
Oh, we are.
Yeah, all
I
the
did
way up,
notice that.
starting this evening all the way up till like tomorrow at supper time or something.
Probably blowing snow because
It's a possible blizzard if you're in the open country out of the city or something, right?
Yeah.
Ground blizzard effect.
For those that don't know, you get out on the flat plains around here, and all of a sudden the wind kicks up and the snow comes up, and yeah.
Yeah, I mean, this is the time of the year where we have the most trees in North Dakota and Grand Forks because they're Christmas trees.
Okay, Christmas tree.
There's nothing outside that would block the blowing snow.
I was wondering if they were Mr. Trees. Mysteries.
Yeah.
Yeah.
Anyway, so today we're going to talk. We had a guest the last couple podcasts, so this gives us an opportunity today to maybe catch up on some of the news that we've hearing about lately. So we want to start with the first item.
Okay, first item.
Ready to go.
Voyager is alive.
Yeah, so we've talked about this a couple weeks back, and the idea was that Voyager had gone quiet, Voyager 1.
Right.
And it took some digging for scientists to figure out what happened. And there's more of the story I found out since we talked about this. So what happened was that command was sent to Voyager 1 to turn on its heater.
Oh.
Because right now, believe it or not, I mean, the power that comes to supply the electricity for Voyager 1 is the radioactive decay of plutonium.
Right.
So there's a certain finite amount of plutonium that was put on board the spacecraft when it was launched back in the mid-1970s.
And I think for the isotope, it's right around half-life now. So it's running on something like 70% power.
Yeah, so they estimate that every year now it loses about 5 watts of energy.
Okay.
So this radioactive plutonium decays over time, and so the amount of energy you can generate goes down.
Mm-hmm.
But that's known. I mean, you're so far away because this is a spacecraft that the purpose was to go out and explore, the outer planets, Jupiter, Saturn, Uranus, and Neptune, and then continue on because it's reached escape velocity to leave the solar system and essentially go into orbit around the center of the Milky Way, go into interstellar space. So there's no way you can use solar panels and try to generate electricity from the sun because you're getting further and further away from the sun all the time, and the amount of energy that would fall per square inch, let's say, of area, greatly declines. And so you'd need like a huge solar panels to generate a appreciable amount of energy when you're out where you are.
You need solar panels so large that they'd work more as solar sails.
Yeah, well, that's it. So maybe that would aid in getting away from the sun,
faster,
right? That photons are pushing it. And anyways, so they decided to go to radioisotope thermoelectric generators.
Mm-hmm.
So they just used the thermocouple process.
So go into that.
Yeah.
So you're using heat between two disparate metals or alloys, and when you do that, you heat one differently than the other, you can produce a current.
Yes, so you can think of an ammeter that's hooked up on a wire, and you have another wire that's twisted on the ends of that original wire. So you make sort of a squashed loop, the ammeter being on one of the wires. And if you take one of those pieces of metal, of those junctions where the two pieces of wires are joined together or twisted together, stick it several feet down in the ground, and then have the other end sort of sticking up above the ground, that difference in the temperature, right, gets reflected as the
As a
flow
current.
of electrons through that wire.
Right.
So that's the thermocouple process that you can use to actually measure temperature down several feet into the soil, which they do. And so in this case, you can heat up one end of the thermocouple with the decay of the plutonium, and the other end could be exposed to the vacuum of space. So
Right.
it's the temperature differential that you want here. That generates electricity, so you get a flow of electrons, and that can run your instruments. Well, there's 4 instruments still running on the Voyager 1 spacecraft, believe it or not. And this was launched like in 1977.
Right.
So it's nearly, almost 50 years now. It's like, 47 years or so that these instruments have been running. And the 4 instruments are given there, as you can read. One is the Low Energy Charged Particle Experiment.
Okay.
One is the Cosmic Ray Telescope. The other one is the Triaxial Fluxgate Magnetometer. Sounds like something from Back to the Future, flux capacitor. Right? And the fourth one is the Plasma Wave Experiment.
Those last 2 are really the important ones right now, aren't they?
They are, well, the low energy charged particles, if you measure, that's the low energy side like of cosmic rays.
Okay.
So that's interesting. And then the Cosmic Ray Telescope itself, of course, can measure a much wider range of energy.
Right.
of the
They're all interesting.
Yeah.
But these last 2 are giving us the outer envelope of what's going on at the heliopause.
Yes, and that's what the heliopause is.
Right.
Do you want to explain that, by the way?
Okay, that's where the sun's electromagnetic influence ends, where the solar wind dies down to background for the galaxy. So we're kind of seeing where the sun's electric field and magnetic fields end their extent.
Yes, so the magnetic field that the sun, I should say, generates extends outwards to the outer solar system. Mm-hmm. And at some point, and that gets weaker and weaker with distance from the sun. So that affects the influence of charged particles that's raining in from all different directions from space itself. And once you get outside of that bubble, if you think of it that way, then you're into the direct effect. If you think about the average of all the stars that are around interstellar space, and the Voyager spacecraft have crossed that imaginary boundary.
Right.
And so now we can directly measure sort of all the overall average of charged particles and magnetic field of not only the background of stars, but the galaxy as a whole in that sense.
Right.
And less affected by the sun's direct influence.
That's it. And, it also kind of like Earth's magnetic field acts as a shield for us against charged particles. The sun's magnetic field does much the same thing. It takes really energetic cosmic rays to get through the sun. Well, that also bleeds off a lot of their energy. And then the Earth's magnetic field bleeds off more, plus the atmosphere, and very few reach us, which is a good thing.
Now, the energy supplied by the radioisotope thermoelectric generators has decreased to the point now where these 4 instruments are operating in a much colder temperature environment than what they were designed
Oh,
for.
so that's why they needed to turn on the heater.
That's why they cycled the heater. And when they cycled the heater, the fault protection system on board the spacecraft, the
Okay.
computer, seeing that it would require too much energy than what it can supply to run the heater as well as everything else. So what it did is it turned off the radio transmitter and switched it to a lower power backup
Transmitter.
mode of transmitting, which is known as the S-band. So normally the communications with Earth is with the X-band, and the X-band provides a much shorter wavelength, therefore higher frequency, so the data rate is greater than the backup S-band transmitter. So when it automatically switched, which was the proper thing to do, the power level was too low, the computer recognizes that, switch from the X-band to the S-band, because there really isn't anything else it can really turn off,
Right.
you see. So when scientists tried to communicate with it, they couldn't because the transmitter was turned off. And what they realized is that Voyager was sending out pings, right, in the S-band. So they had to reconfigure their system to look in the S-band.
Okay, turn off the heater for a little bit.
Right. And then they had brought it back now. The X-band now transmitter is working.
Okay.
So this is the update.
Yeah.
And all of this stuff is done, remotely. I mean, the spacecraft itself is the furthest man-made object from the sun, and it's about 15.4 billion miles away.
And about 15 light hours.
Yeah, it's on the order of that. I think
or
it's more like
20,
20 something.
20, yeah.
Almost a day, almost a light day away.
Right.
So so to communicate with it's very slow, right? If it takes you, let's say, a day to send a signal, have it arrive at the spacecraft, the spacecraft does something, then sends some reply back. You got to wait a whole day for that to get back. So you're going to be waiting 2 days at least to see the result of what you're doing to the spacecraft. And of course, it's so remote, you've got to be very, very careful in what you send. So any command you send up to the spacecraft better be well thought out.
Because you're probably not getting any take backs.
Please turn the S-band transmitter off. Next statement, turn on the X. Oh, wait a minute.
Oops.
The radios turn off completely. It's not going to receive that second command to turn on the X-band.
Right.
Maybe we should tell it to turn it on first and then turn off the S-band, you
Right.
see. Yeah, so you have to be very careful in your sequencing there. But it's interesting to note that we can still do things to the spacecraft. We can repair it essentially.
I'm got to admit, I'm sitting here wondering which of these 4 is going to be the next one to be turned off.
Well, that's it, right? They've turned off other instruments to save power. They've been doing that, all along here since the spacecraft, has finished its exploration of Saturn. So Voyager 2 was the one that went on and observed Uranus and Neptune, and it passed Neptune in 1989. But Voyager 1, you can start turning off the cameras because there's nothing really to photograph.
Right.
This kind of stuff. Trying to preserve as much of the electricity as possible. But at some point, even these experiments, since they're really operating in a regime that they were not designed for, which is not unusual. I mean, a lot of things.
We do that.
Well, think of the Martian rovers, right? They were up there only designed for 90 days or something?
And went on for 15 years.
Or 9
like
years
that.
at least, or something like that. So we've had that happen before. It's not that unusual. But you hope that when you design these things, even though you have to put a time on it, this was designed to last 5 years, that maybe you can get 10 or even 15 out of the thing.
And instead, we've gotten nearly 50.
Yeah, exactly.
So
we'll see what happens in the future. At some point, we're not going to be able to communicate with the spacecraft anymore.
Right.
And it'll be the same kind of arrangement we have with the Pioneer 10 and 11 spacecraft. The last we heard from them was in 2003.
Okay.
And an interesting thing there is they had to keep an old computer up and running until it finally died because the new computers can't communicate with it. It's different programming language. So NASA had to keep this one room operating with this computer so allow it to communicate with the Pioneer spacecraft until they finally couldn't communicate any longer.
Right.
Then you can get rid of it and use it for something else, right?
Now, I got to admit, I think it would be neat to shut these remaining instruments down for a little bit, and if there's enough power, turn the camera back on for one last shot at the solar system, and then shut the camera
and remember
down.
they did that in Voyager, right? They look back towards the solar system, and that's where you get the reference of the Earth as being a pale blue dot by Carl Sagan.
Right.
So when you see the little, but now I don't know what you would see from the distance of Voyager 1.
You probably wouldn't see anything.
It would be a single
probably
pixel for sure.
Just probably see the sun is my guess.
Yeah, and if you get long enough exposure, it'd be just a single probably resolution element, a pixel.
Right.
I mean, these cameras are not even charge coupled devices because they weren't quite ready yet, right? These are other technology that was used to take images of the planets and so on. So yeah.
I just think it'd be neat to have a picture showing the sun as just a bright star in the sky,
Well, the neat thing that they have done with the New Horizon is you can take pictures of different star fields, match it up to images taken on Earth, and use that baseline as parallax measurement.
Right.
The spacecraft is so far away now, that's a huge baseline.
Right.
Way larger than we've ever used before. And that reminds me when we talked about stellar parallax before, and this is where you can measure the distance of nearby stars due to the shift in position of a near star compared to a background stars that are way more distant. And and when you're looking at it from two different vantage points, it's the same effect where you put a finger outstretched, in front of your face, look at it with one eye relative to the background, then close that eye, don't up the other one, and then go back and forth. You see that slight shift in position.
Right.
So that shift is related to the distance between your eyes and also the distance, let's say, from your nose to your finger.
Right.
The further away the finger is, the smaller is that shift. And that's the same with stars, right? The further away the stars are, the smaller is that parallax, that shift.
Yep.
And so to able to measure distances using that technique to even further weigh objects, once you get to a size of the shift that's just too small to measure, you can increase the baseline. So if
The distance between your eyes.
So in this case, it's from measurements from Earth and also from the spacecraft. That baseline
It's huge.
What's huge, right? I can't remember the numbers, like 100 and some AUs or whatever.
Right.
So that's a huge.
And we have a question.
Yeah, go ahead.
So Bill asks, would it be worthwhile to look back again at this point? And the answer is from a science point of view, no, absolutely not. I'm being nostalgic. Let's get a picture of the sun as little more than a bright star. And to me, that's just from an aesthetic point of view, an interesting
Yeah,
thing.
it's an ego killer, right? Because you
Right.
look back at the solar system from such a large distance away, and it looks like just a pinpoint of light in the sky. It's like, are we any different than all the other pinpoints of light
Like,
that you see?
there
Well, we
you
are
go.
because we're life, and we're on one of the planets that go around the sun. But in terms of our cosmic perspective of the size of things, we're just so minuscule, so minute.
Right.
In some sense, so irrelevant.
Yep.
Then
Except I will argue against that because to me, we're the universe trying to figure itself out. You know?
Yeah, so it's interesting there are different ways you can think about it from a philosophical point of view, of course. Yeah, so the Gaia mission, as I mentioned, that's our best sort of space telescope that we have in orbit that are doing measurements of the astrometry of stars and looking at parallax measurements.
Right.
And the latest news I heard on that, Robert, which is kind of disappointing, is it has to maintain accurate pointing, of course.
Absolutely.
And the fuel, if you like, that supplies the thrust to change position is due to run out in next month, in January.
Oh, man.
So the Gaia mission will essentially come to a stop at that point. And it's measured the positions accurately now in stellar parallax to almost 2 billion stars, believe it or not.
Right. I can believe it. But, you know, yeah, I mean, we're talking milli-arc second precision on the position information. So,
Yeah, so it's very, very, very precise.
yeah.
And that's because it's working above the Earth's atmosphere, essentially the diffraction limit of the optics of the telescope. But, you know, with doing this and you can take up the mantle and say, okay, let's come up with an even better spacecraft. And what if I was in charge and had an endless budget in some sense, or nearly endless budget, I would design 2 spacecraft that were identical, so it cuts down the cost of development, and I'd send them in different orbits around the sun. I wouldn't have them hanging around the Earth. And as they spread out, the baseline between them becomes very large. In fact, imagine if one went out to the orbit of Pluto and the other one the same way, but they're separated at any given moment by the diameter of Pluto's orbit, which is about 80 astronomical units.
I would point out that any such orbit would be inherently unstable because of the presence of the planet in that same orbit. But you'd run out of fuel before the orbit would destabilize.
Well, you'd have them in different places of the orbit, so the planet's not even near you.
Right. Well,
Right?
from what I understand, it's
So-
why there can't be a planet on the other side of the sun from the Earth. Is the two of us would destabilize each other.
Yeah, but Pluto's so small; it doesn't have much mass,
Right.
too, and the orbit's so large. The distance from Pluto would
And-
be huge.
And
I
you'd
don't
run
think
out
that's a
of fuel
problem.
on it before.
And I wouldn't rely on fuel. I would rely on solar panels like wings.
Right, like wings, like sails.
and that would adjust your orbit.
Yeah,
In fact, they do that with the James Webb Space Telescope.
yeah. In that case, then the bearings on your gyroscopes to keep it pointed accurately would be the limiting.
Yeah, and if you
Limiting
have a nearly
factor.
unlimited budget, instead of having one gyroscope, you have 5 on board, 4 as a backup redundancy, right?
Right. So when one dies, you kick on another.
Yeah, but that's what you need. You need to get these observation points away from each other.
Yep.
And putting them on spacecraft and have their own independent orbits around the sun. Of course, you could put it on an orbit even further away, right?
Right.
So you can have 100 AU separation or more.
And what that allows us is we start getting to where through geometric means, so not even relying on brightness or anything like that, pure geometry, we can start measuring stars that are at the limits of the Milky Way galaxy.
And this was taken advantage of just a few years ago by the New Horizons spacecraft, which was the one that flew by Pluto in 2015. is that scientists took images of star fields and they compared it to images taken from the Earth, and you can see the shift in position. And you can use that to measure the distance to those stars. In fact, it was a contest they had on the internet where people could download.
Who could get the smallest one?
You could download these images and try yourself to measure the distance to the object.
Nice.
So looking at the shift.
I didn't hear about that. That would have been fun. That would have been a neat class project.
Yeah, for sure. Hey, there's an astronomy lab, right?
Right.
Here are images and figure out the distance to the star, right? So that's kind of cool. So yeah, Voyager 1 is back in the game.
All right.
So that's good, nice update. Now, the other update that we have for you is something we've been waiting with a bated breath all summer.
Right.
And that's the star T Coronii Borealis to go nova. So this is a star.
Brighten up and show up in the sky.
So this is a star in what we call the Northern Crown.
Mm-hmm.
And so it's observable by those who are in the Northern Hemisphere, including here in Grand Forks. In fact, if it's clear in the evening, just after sunset, you can actually see this part of the sky. It's low in the west, but you can still observe it this time of the year. And one of the stars that are in this constellation consists of a white dwarf and a red supergiant.
Mm-hmm.
And the red star has evolved to the point where it has expanded outwards in terms of its physical size, where literally the outer gas of this star is attracted more to the white dwarf than it is to itself.
Okay.
And so some material gets pulled off the red supergiant and ultimately falls on the surface of the white dwarf. And when that can happen to a point where eventually, of course, that material will fuse, and that material is mostly hydrogen. That hydrogen will light up in nuclear fusion reaction, and it will be converted into helium, and it will burn for a short period of time until that fuel is consumed. An analogy is like dumping gasoline on a bonfire. You get this rather explosive type of burning, rapid burning, and then it dies down back to the original brightness before you poured the fuel on the fire.
Now, why doesn't this thing, since this is the start of a type 1A supernova, as we call it, where matter falls onto a white dwarf and ignites the whole thing, isn't it?
No, so
okay.
That type of supernova that you're thinking of, the carbon detonation supernova, that's a situation where a white dwarf accumulates enough material before it would go nova such that it would exceed the 1.4 solar mass limit. Okay.
So before it accumulates enough that it heats up enough and fuses, it goes over the limit and collapses and detonates.
And if you have a mass less than that value, then the electron degeneracy pressure is able to prevent the object from collapsing in on itself.
Okay.
But if you exceed that limit, it can't.
I knew it had to do with the fact that this one was well below the Chandrasekhar limit.
Right. So you just what it does is just compress it, highly compressed, because that's the type of environment that you're looking at here with white dwarfs. And so it reaches the point of fusion where it can burn that fresh supply of fuel.
Right.
But it needs to accumulate material over time. And there are different things you can look at in the system. For example, what is the separation of the two objects? What are their masses? These things are always rotating, moving, orbiting around each other. So what does that look like? How fast are they moving? Is there an accretion disk that builds up? And that's kind of what this artist drawing is showing, accretion disk. In this case, it's enveloping both of the stars, notice. Mm-hmm. So material can be transferred over to the white dwarf. All of these things have to play in the timing of when this occurs. Right. So we have to use historical records. In fact, sometimes we see a star that goes nova. We recognize it because it increases dramatically in brightness. In fact, sometimes by a factor of 100 or so. Mm-hmm. So in some star field, you really don't see anything that catches your attention. And all of a sudden, one evening, here it looks like a new star that's there. And then you can work backwards and say, well, what star actually became extremely bright?
Right.
And of course, it dies down in brightness after a while, and you can be able to see what is the progenitor. You find a way. We know the distance to that star. It was measured through parallax technique already. So you know how far away it is. You can measure the amount of energy you receive and then easily work backwards. What was the intrinsic brightness of the object? What was its luminosity?
Right.
And that would make it different from a supernova when the whole star itself blows up as either a core collapse supernova or as one of these carbon detonation supernova. So you can tell the difference between the two in terms of energetics. So there are some of these nova that occur over and over and over again. So it has to happen on a short enough time scale that we can recognize as human beings that this is the same thing that happened, 100 years ago or 200 years ago, because records were kept, and we can just compare today when we see it go nova to what happened in the past. And that's what happened with this object, right? So this object itself, then, it seems to go off, that has become a nova every 80 years on average.
Okay.
And that's an important, two words there, on average.
Right.
It's not like we time it with our Timex, right? 1 second from now, we're going to see it as a nova. There it is. Everybody go look, right? That's not the case. There's always an uncertainty on when this will occur. So everybody was aware that this was ready to go nova. The 80 years is now up. And so we thought the best chance of it would be sort of in the summer leading into the fall of this year. But so far it hasn't gone nova. In fact, if you go to spaceweather.com, they keep a running tally of the brightness of the star. So people send in their measurements anytime they can, because obviously there's a lot of attention focused on it. So people are using their telescope, making measurements of the brightness of this object, ready for it to see if they can capture it going in the nova phase. And if it does, it'll brighten dramatically. For those who know about magnitudes, it's going to go from about 10th magnitude to about 2nd magnitude.
So it'll be a fairly bright star.
Yeah, so it'll go from an object that you can't see with the human eye, it's too faint, to an object as bright as the North Star.
Right, which is not terribly bright, but
it's easy to see, especially in a dark location.
Yeah.
So that's the kind of thing we're looking for. It hasn't gone nova yet, so people are still studying, because that way you have more information, and more detail about what happened prior to going nova.
Right.
So that you can study it, and of course with space-based telescopes and so on, and all ground-based telescopes. So in some sense, this campaign now of looking at this object is going to provide a lot of details that otherwise we wouldn't have had, up to the point where it does go nova, and then what happens afterwards.
Right.
And when it does go nova, it's expected to be bright for about a week.
Okay.
So if you get unlucky and have 2 weeks of clouds,
oops.
Yeah, you may miss the whole thing.
Right.
So hopefully we'll see what happens. But of course it can surprise us. Maybe it'll stay bright for several weeks, at least long enough that someone here in North Dakota
get some
will be able
measurements
to go have a view of it. So far we're still waiting. That's the update on this system.
Okay. So stay tuned.
Stay tuned.
All right. So next we got some information on the moon.
Yes, you want to make some money, Robert?
Not particularly, but I do want some money, but I don't think I want to figure out how to land on the moon. So
Well, it's not landing on the moon.
Okay.
It's to save lives on the moon. So NASA has a contest that they are running called the South Pole Safety Challenge. And why the South Pole is because that's where we expect Artemis, the next moon landing, to occur, will be in the South Pole region.
Okay.
And what the contest is about, and I'm just quoting exactly from the website describing the contest, is that it seeks a cutting-edge design that is low in mass, and obviously you don't want to have a really bulky thing that weighs a lot on the Earth to send it up into space, costs money, and easy to deploy, enabling one astronaut crew member to safely transport their suited and fully incapacitated partner back to the human landing system. So here's a recognition. And in fact, it was at play in the Apollo project, right? And back in the Apollo days, when people said, okay, we're going to land on the moon. So imagine it's the 1950s, right?
Right.
And someday we're going to land on the moon. And of course, in 61, when John F. Kennedy makes the announcement, the Americans going to land people on the moon, return them safely to the Earth.
This decade.
At that point, we didn't quite know because we just had started the research. And maybe you land on the moon, and it's like quicksand. And your spacecraft goes down, several feet, enough that it's stuck and can't leave the surface somehow. Or maybe it gets tilted. And so when you lift off like the lunar module from the base of it, it's angled in such a way that you can't reach, orbital velocity to get in and hook up with the command and service module.
Right.
So you can think of some kind of scenarios. In fact, imagine landing on a boulder that tips the whole thing over. Oh, we've landed on the moon. Uh-oh, and the thing slowly tips over, right? Then you're done. Unless you can find the strength to tip it back over again.
Right.
Right? I mean, you're basically stuck on the moon forever at that point. So there's all these things you have to think about. Well, includes walking on the surface of the moon can be extremely dangerous. Imagine you're walking along and you bump up against the edge of a rock, and it turns out that that rock is very sharp, like a razor, and it slices open, let's say, your leg of your suit.
Mm-hmm.
How many minutes do you have to get back to the safety of the landed vehicle or some other habitation, right, that can save you?
Right.
Probably very few.
Yep.
And if you're a
That'd be my
ways,
guess.
and let's say you're on a rover or a moon buggy, and you might be several kilometers away.
Right.
So what would you have? Duct tape, right?
Slap hat.
Didn't you watch the Martian movie?
Right.
So you try to think of something that's there for an extreme emergency. And that's what this contest is all about, is to see if there's any smart engineers out there that could come up with some kind of a system that would help a crew member that maybe has passed out from the lack of pressure and oxygen, that you can somehow get hold of this person and bring them back to the safety of the habitat that's on the moon, or maybe the landed vehicle, or whatever it happens to be.
Right.
So NASA's trying to address this obviously safety concern that's extremely important.
And that's a good thing. We do have another question, though.
Yeah.
I was going to point that out before we get to going too far. Wondergoon is asking, has Betelgeuse gone nova, or will it soon?
So it'll never go nova.
Right? It'll go supernova.
It'll go supernova. So
Yeah.
it is a really massive star at the end of its life. And so it's ready to go supernova. So it will core collapse, and the whole thing will rebound outwards in a huge explosion.
Yep.
And when it goes supernova, it'll be extremely bright. And if it's in the daytime sky, it'll be a new sun in the sky. It won't be as bright as our sun, so it'll look like a star, but it'll
Right.
be a new star-like object in the sky. If it happens in the nighttime, it'll provide enough light that you can easily read a book from
That's
the
gonna be
light
crazy.
coming from Betelgeuse during the
Yep.
explosion. Now,
So-
it's far enough away, and believe it or not, there's a large uncertainty on the distance to Betelgeuse. I think the average value that we get is about 500 light years, so it's far enough away. It's not going to cause any damage here on Earth. So it's like watching fireworks, on July the 4th. We can enjoy the display, but not having be so close to it, we're in danger.
That we're on fire.
You're right. So it'll be a dramatic sight. The problem in all of this, of course, is that Betelgeuse can go supernova at any moment. So it could go tonight, and if it does, I get full credit, by the way.
Yep.
Or it could be 10,000 years from now.
It's soon, astronomically.
Yeah, that's
And
the thing.
That's the thing.
So hopefully it will go off in our lifetimes. 'Cause
I'm
it should
hoping.
be very, very
I would-
dramatic.
that would be such a
see
cool
that.
thing to see. That really would.
And it's interesting when you think about supernovae explosions like, core collapse supernova that you get from Betelgeuse. When it actually explodes, do you realize that the vast majority of the energy, like 99% of the binding energy of the neutron star that would ultimately probably get formed at the center, it's not massive enough to collapse into a black hole.
Right.
So it'll probably form a neutron star. 99% of that binding energy comes out in the form of neutrino emission.
Neutrinos, so we don't even see it.
And 1% goes into the ejection of the material, but only 1% of that energy comes out in the form of light.
Right.
So the light,
And in a way, it's a good thing it did, because if it didn't, it would be bright enough to cause us harm.
so the light that you actually see when the supernova goes off represents just a small fraction of the total energy that's emitted from these events. So it's
That's
amazing
crazy.
when you think of. In fact, when the supernova went off in 1987 in the Large Magellanic Cloud, there was a bump of neutrinos that was detected.
That's right. There was.
Right? It was
yeah.
I think it was on the order of 12 or 13, something like that, neutrinos that were detected. So, and they're hard to detect. They have very, very little mass, and they don't have a charge, an electric charge. So they interact very weakly with material. And so, and because that most of the neutrinos that stream through us, like from the sun or from nuclear reactions of different types, including the ones in our nuclear power plant, the fission reactions, those neutrinos go right through the Earth, right through our bodies, and don't interact with anything.
Right.
Just occasionally, they have a head-on collision with the center of some atom, and you'll see the byproducts like the ejection of electrons.
Right.
And
Which
those
will make a nice little flash of a particular wavelength.
Yeah, so those electrons are in these Cherenkov radiation detectors. So those electrons usually travel faster than the speed of light in the water, which is usually heavy water, and they emit this blue light.
Mm-hmm.
And that blue light we can detect, for example, with photomultiplier tubes.
Right. And in answer to your second question, Wonder Goon, how long after the supernova will we see the explosion? If it happens tonight, it actually exploded 500 years ago.
Yeah.
It's 500 light years away, so it takes light 500 years to get from it to us.
Yeah. Just like when you go outside now, if you couldn't see the sun, you're not seeing the sun as it is instantaneously right now. You're seeing the sun as it was about 8 minutes ago.
Right.
Because it takes that long for light to get us from the sun. So when you think about that, anyone you see walking down the street of Chicago, and you look at people, you're not seeing them in your present. You're seeing them in the past, every single one. Because light in the daytime reflects off of their surface of their body. Some of that light gets reflected back to your eyes, but it takes time for light to get there. So you're seeing people in the past several nanoseconds.
Right.
Of every single person that you see.
Now, because your eye refreshes on the order of a few microseconds, nanoseconds means you're seeing them practically as they are.
Yeah.
But,
And when that distance becomes greater, like at the sun or even the nearest star to our sun, Proxima Centauri, if you were to observe that tonight, the light that enters, let's say your telescope left that star about 4.2 years ago. You're not seeing the star as it is today, but as it was. And for Betelgeuse, then the light would have left it about 500 years ago.
Yep.
Now, the other thing I wanted to mention too, or to comment on, is the fact that I mentioned that the distance to Betelgeuse is rather uncertain. And the reason for that, it's so bright of a star. The spacecraft that we have, like Gaia, that can measure, through parallax shift the distance to the star, their detector gets swamped.
it gets oversaturated.
So you can't measure the distance very accurately to these really bright stars like Betelgeuse.
Right.
So we have to come up with a special way of dimming down that light to allow us to do these measurements. But that would be only for a handful of stars, and it really is not worthwhile financially, you see.
Right.
You usually want to have a detector that looks at really faint things.
I was about to say, most stars are faint, so
Yeah.
you don't really want to look at the bright ones.
Yeah. So getting back to
The moon challenge.
the moon thing. So NASA has a contest that's running that anybody, and I didn't see any restriction on citizenship, anybody who comes up with a design, a method, so this would be engineering, if they like your design, then you can win $20,000.
That's nice.
And that's 20,000 US dollars, which in some currency is a lot of money.
You're right.
So they're going to select one winner as first prize. Second prize is $10,000, one winner selected.
winner.
And they're going to select three people for the third prize, each being $5,000. So Robert, if you want to buy that Christmas gift that I know you're dying to buy, but just can't afford,
Yeah.
put your name into here. Think
Yeah.
about it seriously.
Now, because you're being paid this by the government federal agency, does that mean you don't have to pay taxes on it?
I'm sure you have to pay taxes.
Yeah.
Any income, like
Right.
winnings or gambling or lottery, you pay income tax. You definitely would have to pay income tax. Now, for those of you who are seriously looking at entering this contest, you have some time. January 23rd is when it runs out at 5 p.m. Eastern time. So if you have any ideas, maybe you can teleport the injured astronaut right directly into the landing craft.
I think you're going to make more than this prize if you figured out a way to do teleportation.
Just involve quantum entanglement and AI.
Oh, Lord,
and
here
that
we go
should-
again.
Just use those buzzwords and you'll have it, right?
Right.
But anyways, so here's a contest where maybe some of you can win some money. Who knows?
Yep.
Right?
I would be proud to know you. I'll put it that way if you figured it out. So
Now, we spend a lot of talking about supernovae, and we mentioned about black holes. Here's an interesting study that was, well, it's preprint form back in October. It still hasn't been published yet.
okay.
So I checked last night. It's not finished going through the peer review system, so we'll see how this plays. But what it involves is that they discovered a star that was starting to get brighter, and then it disappeared, Robert.
Okay.
It no longer exists. And the idea that people have is that it appears to be a situation which doesn't happen very often, where you have a star explodes as one of these supernovae, but instead of all the material, all the outer envelope being ejected into space, for some reason, and people really don't know what this reason is, no matter what they write in their paper, there wasn't enough energy that was put into the emission of neutrinos. So then the flux, a huge flux of neutrinos that get released during the nuclear reactions in the supernova explosions, those neutrinos, for some reason, don't have enough energy to deposit it into the outer envelope of the star, to cause the star's outer envelope to be blown off completely, like a regular supernova.
So instead, it all falls back in.
It all falls back in, and because you have all that mass falling in a very small volume, it turns into a
black hole.
black hole.
Yeah,
and
it would
therefore
have to happen on a fairly short time scale too.
for sure. So if you want to, so that's what this paper is all about. And so this object was actually found in the Andromeda Galaxy M31. And what we show here is some images taking a light curve, essentially, some measurements taken over a period of time. And that's what you see on the left side. And all of a sudden you see a big drop in the brightness of this object. Essentially, it goes to zero. So it was starting to brighten up like a supernova, and then it kind of reversed and went down to nothing. And the only explanation that these researchers have proposed is that it looks like it collapsed into a black hole. Now, how would you do that? Well, that's sort of shown in the cartoon that you see on the right side, where you see initial shock wave that's generated, and then you see the envelope starting to expand outwards, and then the shock gets stalled somehow. So you have to come up with some interaction that would stall that shock. And then that causes the material then to collapse, to accelerate collapse, right?
Okay.
And then eventually collapsing down to form a black hole.
Would probably form a fairly massive one too, because that's why you don't see stellar mass black holes, above about what 5, 10
Yeah,
solar masses?
so the limit of a neutron star, you could do a thought experiment. Imagine you had a neutron star.
Right.
And you do the thought experiment where you take a little piece of mass, a cube of material, let's say, and add it to the neutron star, a ball bearing.
Right.
Okay? And you keep adding and marbles. Let's go with marbles, right?
Okay.
Everybody knows what a marble is, I'm sure. Sometimes I lose mine, but that's another story. So you add these marbles,
Okay.
and eventually, and you could ask the question, can I do this like for infinity? Can I keep adding marbles and nothing happens except maybe the neutron star gets more massive, more massive? Well, with degenerate neutron star material, when you add more mass to the neutron star, it gets smaller, not larger.
Which is weird for a star.
Which is weird. And it's weird in our everyday experience, right?
Right.
If you add more mass to a chocolate cake, it gets larger, it doesn't get smaller.
Right.
That's the point
Fair,
of probably
fair.
adding more mass to it, right?
Yeah.
Anyways, so what happens in this case, if you do that thought experiment, keep adding mass, eventually when you get to about 3 solar masses,
Somewhere in there, yeah.
the neutron star will collapse in on itself, and that would generate
A black hole.
a black hole. So if you have mass that returns to the center, there's probably, let's say, a neutron star that's in the process of forming anyways, the core. Mm-hmm. And if you add the outer layers on top of that, if it pushes that mass over 3 times the mass of the sun, then it will form a black hole.
Right.
And so we've never found neutron stars more massive than a three times the mass of the sun. In fact, we've never found one that's close to that limit. They always seem to be around 1.9. I think 2.1 or so is kind of the most massive. And some people say, okay, there's a little bit of a misunderstanding of the physics involved here. Why can't we reach 2.8 or 2.9 solar masses? Number one, we probably need to find more neutron stars.
Right. Which are hard to find.
Yeah. And you can find them as pulsars, but it's hard to measure their mass. That's the problem. So
Right.
we know there's over 2,000 pulsars, which are neutron stars, but there's only a very few systems that we can use, like Kepler's third law, to find the mass of the neutron star.
Where they're in a binary.
Yeah. And so maybe the statistics, just small number statistics, we're working against here, right? Once we find a large number of neutron stars that we can measure mass, maybe that'll fill in some of that space, you see.
Right.
Or maybe we are missing some physics, because we're talking about very exotic type of physics here.
Right.
Nuclear density and greater of this type of material. So do we have a complete understanding of how things actually operate at those sort of high densities, right?
But,
Question mark on that.
Right. And the thing is that most core collapse, you get a supernova that blows away most of the material. So that's why you actually, even though you have an 80 solar mass star, you'll end up with a black hole that's only 5 solar masses. because most of the material got just
Yeah, so we're
blasted.
talking what's left over in the core.
I'm imagining that something like this would produce a fairly massive black hole because you don't have everything being blasted out.
And that's one of the great unsolved mysteries in cosmology today, is why do you get these really supermassive black holes?
Right.
Like our Milky Way has one at the center, 4 million times the mass of the sun. How do you form that? You can't form it from a stellar mass black hole, and not even close to being such a high amount of mass. You can merge a bunch of black holes together, but where's that going to happen, right? That you need a huge number of them to make 4 million. And the supermassive black hole in the center of the Milky Way is a low ball guy, right? Low mass guy. The Andromeda Galaxy has one billions of times the mass of our sun. So how do you form that?
How do you form that?
And you need a short period of time to form, by the way. You don't have the history of the universe to do it.
Right.
So it has to happen on a fairly short time scale.
The galaxies that are actually fairly far away still show the presence of these things. So they formed fairly quickly after the formation of the universe.
Lots of stuff to study, Robert.
Absolutely.
Lots of stuff. Now, the other thing that's kind of neat is an image that was released not that long ago, just a few days ago, from the James Webb Space Telescope, but from perspective point of view, I want to show you the Hubble Space Telescope image of this galaxy. It's known as the Sombrero Galaxy. It's a distance of about 30 million light years. It's a beautiful example of what we call an SA type of spiral galaxy. It has the disk, which is nearly edge on, and you can see the interstellar matter that's in the near side of the disk to us, all of that dark band that you see there. That's us, right? That's dust. That's what the Earth is formed from. That's what ultimately we came from. So interstellar matter, like the gas and the dust, is important, right? If you want to have life in the universe as we know it. But the disk itself, you can kind of see a little bit of the disk and make out carefully the spiral arm-like structure. They're wrapped up really tight.
Yep.
And the bright area that you see sort of in the center area, that's the bulge of the galaxy, that's fairly bright, right? That makes it an SA type, a really bright bulge area and tightly wound spiral arm.
Most of that spherical distribution is that halo is really just glare from that center, isn't it?
No, that's stars.
It is stars.
That is stars. So that's a huge number of stars that make up the bulge of this galaxy. In fact, it has a very large population of globular clusters.
Okay.
Now, why I'm showing this is because the James Webb Space Telescope, which operates at infrared wavelengths, recently observed this galaxy. And here it is here. And what you can see is, number one, the brightness of the bulge greatly diminished. So that was mainly an optical light. When you go to infrared, most of those stars are not big infrared producers. They would be very low mass stars, low surface temperature stars. And that's not what the bulge is made up of. But what dominates this image is the disk part, right? That's in that the spiral arms will be embedded in. And what you're seeing here essentially is dust that's in that disk.
So it's being heated and glowing in an infrared.
Yeah, so dust gets heated up. Anytime you heat up dust, it loves to emit at infrared wavelengths.
Yep.
And the heat source, of course, is the stars that lie within the dust,
which are operating mainly in optical.
Right, and don't forget, it's the gas and the dust, the interstellar matter, as we call it, where stars are formed from.
Right.
So if you have lots of interstellar matter, you have lots of ongoing star formation. And those stars then can cause the dust that they're embedded within to heat up, and we can see that easily at infrared wavelengths. So this is a very high-resolution infrared observation of the Sombrero Galaxy. And to me, it looks beautiful. I mean, it's just gorgeous. Amazing when you think about it. In fact, if you look at the top and bottom of the disk, you can see separate pinpoints of sources of light. So they are probably cooler stars. And even some globular clusters, it looks like. I wouldn't be surprised they're above and below. So there's a study. You can take these images and measure the brightness of those globular clusters at these infrared wavelengths from the James Webb Space Telescope observation. But speaking about cosmology, the other thing that recently came out is a new simulation, the largest cosmological simulation that's ever been produced on a computer. So this simulation was generated by what is now the second fastest computer in the world. It was, when it started, it was the fastest.
Was the
And
fastest.
people are evolving. So there's now even another computer at one of the national labs that's even faster than the one that was used to generate the simulation. This was done at Oak Ridge National Laboratory. Now here is some information as you see they're written. This computer is so fast, and what's the punchline you're supposed to ask me?
How fast is it?
It can run or perform 1.1 times 10 to the 18 floating point operations per second. That's 1 followed by 18 zeros.
Right. Wow.
Isn't that amazing?
Or 1.1 or 11 followed by 17.
Now, the fastest one is about 1.7 times 10 to the 18.
Okay.
But it's just,
It's unbelievable.
It's
That's
incredible, the
ridiculous.
advancement of technology. Now, what do you need if you want to build such a computer? You need, this one has 9,472 AMD CPUs.
Wow. 9,000.
Not Intel,
9,500.
not IBM, but AMD
Yep,
CPUs.
9,500 desktop computers.
It has, and on top of that, it has 37,888 AMD graphic processing units, GPUs,
Right.
all running together as this big mega supercomputer.
But you can play some real good video games on that thing.
I can imagine how it would speed up my work running it on this.
right?
Now, the simulations that you see there, there's one in the far right, that is the size of volume of space shown in a galaxy cluster. That's, for measurements of distance, it's a cube. That's or almost a cube here. It's 64 by 64 by 76 megaparsecs. Now, a parsec is 3.26 light years, so a megaparsec is 3.26 million light years. So you multiply that by either 64 or 76, depending on the dimension you want to look at. But this volume of space, which is incredible, it shows you a lot of nitty-gritty detail of the galaxy cluster that's forming under the gravitational collapse of material. It only represents 1/100th the total volume of the simulation itself.
Oh, wow.
So that's, I mean, to download this data and even make cubes like this would be difficult, right?
Right.
Hopefully they have some way of parsing through the simulation to make it a little easier to download. But
Yeah, I'm sitting here marveling at the heat that simulation would have produced while it was running. I mean,
too bad you couldn't use the
Wow.
thermocouple generate like
and send it out to Voyager, right?
No, I was gonna
Oh.
say, and then power the nearby city.
Right? Yeah.
Imagine the air conditioning that you need to cool this sucker.
That's
right?
it. This is why.
Wow.
Google and others are looking into submerging in the ocean their big data centers. So
Yeah, it's unbelievable when you think
Yeah.
about this.
it's crazy.
Yeah, for sure. Now, there's been other news too.
Okay.
One of the ones I wanted to mention is so we know right now the Vera Rubin telescope, which is a brand new telescope that's constructed in Chile. It's about 8 meters in diameter, and it's a fast telescope in the sense that it can survey the whole sky above the observatory, so the
Okay.
southern hemisphere, and cover it completely in 3 nights. So every
That's
3 nights,
crazy.
and every 3 nights they're going to go back and re-image the sky
Right.
over and over and over and over and over again, and they're going to do that for at least 10 years and probably beyond. Right? So this large survey of a huge swath of the sky, essentially half the sky. Now, this telescope, which is first it was known as the LSST, so it's been renamed in honor of Vera Rubin, and so the project, if you want to call that, is the Legacy Survey of Space and Time. Now they had to use the same LSST to make up different words for what that actually means now. So they changed that a little bit. So they're going to essentially image the sky, and that was supposed to be released publicly. And at first, they were talking about releasing it immediately. Well, if you're releasing data, right, a wide field imaging camera,
Right?
and taking data over 3 nights, how would you download that, number one? Even with, 1 gigabit sort of internet
I mean,
flow,
we're probably
it's-
talking petabytes of data.
You are talking petabytes of
Okay.
data.
So yeah, even at a gigabit rate, that's going to take days.
Yeah, so it'd be like, you can have the data if you want, but what does that really mean?
Where are you
right?
storing it?
Yeah, you need some way. So there are different science collaborations that built up over time. I'm a member of some of them that are working on different algorithms to process the data to try to get some information out of it. It's like you're going to be drinking from the fire hose analogy.
Right.
There's going to be so much data coming at you. But the thing is, if you're looking at the sky, you're not just getting astronomical objects in your telescope. You're getting anything that's above the horizon.
Yep.
And this everything includes satellites.
And asteroids, meteorites.
Includes, just stick with the satellite.
Okay.
It includes a certain class of satellites that are not supposed to be there. Nobody knows they exist.
Right.
These are the spy satellites that are different
I didn't even
agencies.
think about those.
Hey, we got to watch the door, keep it locked, make sure nobody comes here while we're talking about it. This was all released publicly, by the way. A story came out just 2 days ago about this. So what has happened is that certain agencies which don't make themselves known,
Right.
they go through another federal agency, the National Science Foundation, and said that this other entity that exists, black op type of thing, right, has not requested. That's probably too soft of the word.
They've been told.
Yeah, demand is probably closer to the right adjective to use here, right? That they highly, highly suggest that you do not release this data publicly immediately after it comes off the telescope, which is what I thought the whole project was about initially.
So they can go in and pipeline and redact certain information?
Yes, exactly. That this information is going to go to the certain agency in the federal government. They're going to look at the images. If any of the images have captured any of their spy satellites, they will take out a postage stamp of the imaging data and then release that image to the astronomers with this missing data.
Like astronomers would be able to figure out where the postage stamps are.
No, you know where the postage stamps are, but if you make the postage stamps large enough, that's enough uncertainty in the position that you're not going to be able to accurately track the orbit of the satellite around the Earth.
Got it.
Okay? And then the agency has agreed that they will allow astronomers to release the full image without the postage stamps taken out about 3.5 days later. Initially, they wanted to wait a week, but the LSST scientists on the project are negotiating through the NSF to say, can we do 3.5 days? And it turns out that if you try to mathematically calculate the orbit of these satellites based on the missing data, over a time span of 3.5 days from the real data where you see the object, given where it was 3.5 days ago, it's too large of a time base, temporal change that you can't
function is.
You can't accurately predict the location of the satellite at any moment going forward. And the other thing is that the agencies, what they do, I guess, is they actively change the position of the orbit of these satellites all the time. So if some other foreign country, an adversary, is trying to track where your spy satellites are in order to target them in the future, their orbits are constantly changing. So it's a cat and mouse game all the time. So it's interesting to note that now they're going to redact this data from the LSST, and we will not see in real time
where these things are.
And the other thing that came out recently, it actually just came out today, is a study has been released using measurements of water from the comet that the Rosetta mission studied. I don't know if you've seen that in the news today, comet 67P. And what they just found was that the water, and they analyzed by looking at the deuterium to hydrogen ratio, is as what we have here as water on Earth.
Oh,
so in the old days, in the old days, we thought that comets supplied the bulk of the water on Earth, and then when they measured the deuterium to hydrogen ratio, it was different in comets than what it was on Earth. So it can't be that. But now we found examples of at least one comet where it is a match to the water's deuterium to hydrogen ratio. So we're back to this again, that water may have come here from comets. Just not from every comet, for certain comets.
Right.
And if you want to find out more, this stuff is interesting to you, of course,
come to the University of North Dakota, and we got several programs that are completely online, so you don't even have to come and enjoy our winners. But if you decide to, it's a great place to come. So
Now, the next podcast will be next Tuesday, December the 10th. We always leave you with a quote at the end of our podcast. Today, I decided to get a quote from Dr. Edward Stone, he passed away, unfortunately, in June of this year. He was the Voyager project scientist from 1972 to 2022.
wow.
It's amazing for that length of time.
crazy.
That's like
Yeah.
50 year. He was the project scientist. So here's what he said. Voyager 1 is the most distant object made by human hands. We've never entered the interstellar medium before or actually sampled interstellar space before now. It is another first in the history of exploration that includes Ferdinand Magellan's first circumnavigation of Earth, the first planetary flyby in 1962 when NASA's Mariner 2 went by Venus, and Neil Armstrong's first step on the moon.
Nice.
Thank you very much for watching. Please give us a thumbs up.
Thank you, folks. See you next week.